Welcome to the 8th chapter on events and responses of the Logical Foundations of Cyber-Physical Systems textbook. We have already understood the important analytical implications of control loops in the previous chapter, but this time we'll want to understand their impact in important design paradigms, the one that is called event-triggered control systems, where the idea is basically that your controller responds to certain events whenever they happen, and keeps on executing the event detection in a control loop. A safe controller in event-triggered design principles is one that uses the appropriate response for each of the events of relevance. The advantage of event-triggered control, also called event-driven control, is that you have pretty simple safety arguments. All you need to do to convince yourself that the controller is safe intuitively is to list all the events of interest and make sure you have an argument why you respond in the correct way to each of them. The downside of event-triggered control systems is that they're fairly hard, if not even impossible, to accurately implement. Overall in this chapter, we will see a number of very crucial modeling lessons for cyber-physical systems. Why are we talking about this? Well, we've seen control loops in CPS models in the 3rd chapter. We've seen unwinding loop principles, iteratively unwind loops one at a time in the 5th chapter. We've seen loop invariants finally in the 7th chapter, which has been a lot of attention on loops, but that's not a coincidence because indeed loops are one of the most difficult challenges in CPSs. Besides differential equations. Differential equations are also challenging in CPSs. In fact, if both are simple, so if the differential equations are simple and there are no loops, CPSs all of a sudden become really easy. They're even decidable. In this chapter now, we will focus on how these two difficult parts of a CPS interact. How do loops interface with differential equations? And of course, that connection is ultimately the link that ties the cyber and the physical part together. There's two ways of tying cyber and physics together. One of them is event-triggered control, where the responses to events dominate the behavior of the system. The other is time-triggered control, where you periodically perform actions. In both of those paradigms, time-triggered control and event-triggered control, follow naturally from an understanding of the hybrid program principles. And here, in this chapter, we're looking at event-triggered control, which includes a number of very valuable modeling lessons. Speaking of modeling lessons, on the modeling and control side, we will understand a lot about modeling cyber-physical systems in this lecture by zooming in on the fundamentally important control principles of event-triggered control, where you're working with a continuous sensing assumption and provide the appropriate feedback mechanisms whenever the events happen. And it turns out those feedback mechanisms can actually be rather subtle. This is one way how the control and the physics parts interact. On the computational thinking side, we're zooming into rigorous reasoning techniques for CPS loops with invariants, not because we're dreaming up new ones, we've seen them in the previous chapter, but because we're using them for a lot of good. In particular, we'll be investigating subtleties of hybrid systems models. We will only look at how subtle this is already in a very intuitive, simple example. We'll be adding control decisions to the bouncing ball to turn it into a vertically moving ping-pong ball. That retains the intuitive simplicity of the bouncing ball, but it gives us generalizable lessons how we design event-triggered control systems correctly. It's not possible to claim that this would show you how to verify CPS models of really seriously any appropriate scale, because we're just working with a bouncing ball. But it turns out it is a lot easier to first see how cyber and physics interact in an event-triggered way for the much simpler and familiar phenomenon of bouncing balls because that provides the exact same generalizable lessons, but in a much simpler setting that we can easily understand and relate to. Oh, wait a second. Bouncing balls didn't have any cyber part, remember? Quantum, the bouncing ball, didn't bring his computer, but that's fine because he still features the exact same hybrid systems dynamics that are typical in cyber physical systems. On the CPS skill side, we'll understand the precise semantics of event-triggered control, which is really not so easy and something that many people struggle with. So it's important to get this exactly right and precise in a hybrid programs context. It's comparatively easy to see what's going on. From that, we'll develop an understanding for the operational effects, and we'll see for the first time in this course the principle of model predictive control in action, where you're basically predicting what your model is doing and then control it correspondingly. But there's a lot more to be said about this principle. So, let's get going. Let's understand the need for control. We've seen the bouncing ball, quantum, which is a provably safe bouncing ball, but it's also a pretty bored bouncing ball. I mean, it's very safe, but all that the bouncing ball is doing is just bounce from the ground and bounce from the ground, bounce from the ground, bounce, 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 bounce. Well, it's cool that quantum, even with a proof, was able to identify under a number of assumptions that all the behaviors of his repeated executions of continuous differential equation followed by control and again and again and again made sure that bouncing ball quantum is always above ground and below the initial height. Proof is a pretty strong evidence of that, but it doesn't do a whole lot of exciting things in there. In fact, quantum never reaches any decisions whatsoever in it. Even if there is a controller, the controller is basically just modeling what happens on the ground when the bouncing ball is being bounced back up. So, for example, when the bouncing ball stops evolving the differential equation, then, well, there is a choice, but the choice on the left-hand side is only available when the bouncing ball is on the ground, and the right-hand side is only available when it's not. So there really actually never is a serious decision. And if it is on the left, exactly one thing happens. It's being bounced back up with the velocity negated with a damping factor. And on the right, no action follows. And speaking of damping coefficient, we actually were only able to prove it in the case where the damping coefficient is exactly 1, in which case the behavior is bounce and bounce and bounce and bounce and bounce and that's not super realistic, but on the other hand, it gave us an easier proof by this invariant. But this is not a fundamental assumption, it's just one that made our proof a bit easier. So, but even coming back to that, there is no actual control choice. In other words, once we've identified the right requirements for when is it safe to start the bouncing ball, we just let it go. Now, quantum is bored of that. He wants to be given more say over what's happening. So imagine quantum, the bouncing ball, is picking up a ping-pong paddle to exert control over itself by patting himself over the head. So basically the idea is that quantum, the bouncing ball is falling, it's still bouncing back from the ground, but in some range, let's call it 4 to 5, does the ping pong ball have the opportunity to use a ping pong paddle to hit itself over the head so that the ping pong ball will be shooting back down, bouncing back from the ground. Again, between the range 4 and 5, the quantum ping pong ball has a chance to use the ping pong paddle when it's bouncing vertically, hit himself over the head so that again it's shooting back down as opposed to flying further up. Well, don't get any ideas about this admittedly rather Munchausian effort of the bouncing ball hitting himself over the head with the ping pong paddle, which really by the principles of opposing forces shouldn't do a whole lot. So fine, right? Imagine instead maybe that the ping pong paddle has a controller that is independent and can be used within the range 4 to 5, and the quantum ping pong ball has a little button it can push to use the ping pong paddle's control, which will make it push down. But who would ever be distracted by these kind of little Munchausian details? For our story, the only thing that is important is that we do give more control to the ping pong ball model. Let's do that. So how do we say that within the range from 4 to 5, there is an extra control choice? Well, an extra control choice, that sounds like having more of a choice here. So let's add an extra choice in where, well, of course, this choice is only available if we're presently between height 4 and height 5, between the two red lines here. And what then happens is that the bouncing ball, has its velocity again inverted, but this time by something like a damping factor. It just doesn't actually literally have to be damping. You could actually put energy into the system. So it's just some number f that is a constant greater or equal 0. Damping factor equals 0. That basically is just a barrier that makes the velocity go to 0. Eats up. It has no reflective property. And f equals 1 means it's just being bounced back up straight out without any additional energy or energy loss. And f equals, let's say, 100 means it's shooting back down real hard. Okay, we've developed a hybrid program with more control. All of a sudden there's more of a choice. Super filled and exciting. I guess the next thing we need to do is ask ourselves whether the proof still holds true. Is it still valid that all behaviors of this model have an extra choice, make quantum stay in between the bounds? This time, the initial height is supposed to be between 0 and 5. So the remaining question is also whether ping pong ball quantum is between 0 and 5. Of course not, because it's an extra choice that the system has, but there's no reason to believe that it will ever be executed under the appropriate circumstances. So what we need to do is we need to ask ourselves, every time we design a CPS controller, whether we actually believe that we've designed it correctly. And we basically follow René Descartes' principle of the Cartesian demon that he invented in 1641. What he said back then is he asked himself from a philosophical perspective what it is that he can really know. And he questioned everything he ever saw and only accepted things for true that he had reason to believe. That's a pretty skeptical perspective on life. But it was useful for him because it allowed René Descartes in the Décode de la méthode to find out what science by and large can still believe in. And for example, he settled on a famous, very small piece of knowledge that even if the Cartesian demon is tricking him and he's seeing things that aren't really real, and it's just a demon that is providing sensory inputs to him, that still, even if all of this would be the case, that he himself, René Descartes, would still actually exist because, well, he was at least the one who was being tricked into illusionary sensory inputs. That is where the famous cogito ergo sum, so I think therefore I am, comes from. But we're not adopting that strong of a skeptical principle, but we only face a lightweight Cartesian demon as an opponent by making sure we doubt the correctness and safety of CPS controllers until we have appropriate evidence that they're okay. And the best form of evidence is, of course, the mathematical proof that the models are safe. If we look at the daring ping pong ball model, we ask René Descartes and his demon for help with the proof. Is it safe? No, it is not, because the extra control choice is merely a choice to be taken, and we don't have to take it. For example, what's perfectly possible is that we're falling according to gravity, the differential equation stops, we're on the ground, so we act like this. We are flying in the differential equation after having repeated back up again. Then we could stop the differential equation at height 4. We could then run the choice and go for the ping pong ball action. So hit the ping pong ball over the head, which will shoot down, and again at the latest here it will stop the differential equation. It has a bunch of options, but really in this case only one, the one that says your height is exactly 0, so it is inverting its velocity, and the loop repeating differential equation follows. We fly back up, but if we're here, for example, even if we stop the differential equation, we could go for this choice, because we're not on the ground, so it's perfectly possible to run this choice. So right here, for example, we could run the choice to do a test whether x isn't 0, it isn't 0, and then do nothing of the sort of anything. Repeat, and of course we will keep on flying, and at the latest up here, Quantum will panic because he's higher than the initial height 5 that he was supposed to never go above. Remember, Quantum is an acrophobic bouncing ball. He wants to bounce faster with the ping pong paddle, but he doesn't want to bounce higher despite the ping pong paddle. Okay, no problem. We can fix this by augmenting the test whether we're on the ground to say this test is only supposed to be possible if we're not on the ground, but also don't run the event at the moment. Right, so if you're not between 4 and 5, only then is this no-op a possible action. So even if René Descartes says the previous model was unsafe, the modified one should now be safe. But it isn't safe, because what's still possible is that you could still miss this event. How could that happen? Here, this discrete control says that, well, we're only allowed to skip this if we're outside the event between 4 and 5, and we can only run this when we're between 4 and 5. And that choice is only possible on the ground. So how could we possibly miss this event? Well, we still can, right? Because the duration that we follow the differential equation is completely non-deterministic. We could follow the differential equation for any amount of time, for example, until here. At this point, notice that if we stop the ODE, that option is not available, that option is not available. No, only this one is available because we're outside the bounds, but wait a second, we're already outside the bounds and above 5. So that's an unsafe evolution right there. Okay, I guess we just have too many choices here, and that's probably the mistake. We should have used if and else conditions, a proper if and else statement that says if we're on the ground, we bounce back up from the ground, else if we're in the event zone between 4 and 5, we absolutely have to run the ping pong paddles control, and that also means else if nothing actually happens. Oh, well, that may be clearer modeled, but it's also just as clear that the model isn't a safe one, because if we ask René Descartes and his demon for a proof, the demon wins and says, no, the model is still unsafe because it could, run like this, fly back up, use the ping pong paddle, fly like this, fly back up, because you can follow the differential equation for any amount of time, all the way until here. And even if the discrete controller would do the right thing if it ever would be asked to execute, there's no reason to believe the differential equation would stop. When does the differential equation stop? It's only guaranteed to stop when the evolution domain constraint hits. Ah, I get it now. I guess we need to put the event inside the evolution domain constraint, because even if an if is an if and else, we can still miss it. And that leads to the model of event-triggered control, or event-driven control, where we're augmenting the world with constraints on how long it's allowed to evolve, because we're interested in particular events that happen, and then our discrete controller is responding to them in the correct way. So let's do that. Let's remind ourselves about the role that evolution domain constraints play in differential equations. The differential equation x prime equals f of x within Q, so we follow the differential equation where the time derivative of x is the value indicated by the right-hand side of a differential equation, but we can never leave the domain where Q is true. So in pictures, we can follow from time 0 to time r, while always listening to the differential equation, but also always make sure at every state that we reach along this evolution, are we inside the evolution domain constraint, Q. And of course, we can stop it still at any arbitrary early point because the duration is non-deterministic, but there's no way of going to this point, for example, because we would have left the evolution domain constraint before that. So if we use this evolution domain constraint to help quantum the ping-pong ball, let's put more constraints inside the evolution domain constraint to make sure that physics pauses and the discrete controller actually is being run. Here's the event we're interested in, that the height is between 4 and 5. So let's put that inside the evolution domain constraint. This is now very stupid, because we can say we can follow the differential equation for any amount of time as long as the height is above 0 and as long as the height is between 4 and 5. But all of a sudden this physics doesn't let the bouncing ball ever go below height 4, which is certainly counter-physical. I mean, this would be a good model if you would, put a big floor here and a big ceiling there, but that's an entirely different world that we're talking about all the moment. Well, and come to think of it, this is broken physics because it's the event that always is assumed to happen in the evolution domain constraint of a differential equation, but we also did it differently on the ground, right? What we did is we said basically augment the differential equation with the domain of interest, x greater or equal 0, so bounce arbitrarily above ground, never fall through the ground. But the controller only listens for the boundary of that. It only listens for if we're literally on the ground down here. Then we need to run the control. And if we're above ground, that's perfectly fine as far as the evolution of differential equation goes. The limiting point is what we have as the control, and anything above is what we have as the evolution domain constraint, because we certainly would like the ball to keep flying here or there freely. So let's do that in the same way, also by putting the limiting constraint as the event in the evolution domain constraint. So now our evolution domain constraint says we're always above ground, but below height 5. And now if we ask ourselves whether we can prove this, the answer is yes. René Descartes tells us that the system model is a safe one. It always makes sure that you're above the ground and below height 5. Yippee! Okay, so René Descartes told us that this model is safe, but he should have told us no. In other words, by putting x less or equal 5 into the evolution domain constraint, which is the upper limit of the event, we may very much miss the lower end of the event, that we're already above 4. On the other hand, under no circumstance whatsoever will the physics be allowed to miss the upper end of the event, the 5. So at the latest, at the point 5, will the evolution domain constraint make the differential equation stop, so that the discrete control runs, and the discrete control will then check whether the position is between 4 and 5, which, for example, it is here because physics stopped a bit early, but it certainly is here because physics stopped at the extreme, so we'll hit it over the head here and here and here and there. The physics may miss the lower bound 4 of the event, but it is impossible for physics to miss the upper end 5 of the event. So again, we'll ask René Descartes and his baby version of the Cartesian demon, whether this model is safe. So the property is indeed true that we're always between 0 and 5. And indeed, René Descartes says yes, the differential logical formula written down here is valid, and you can even find a proof for it. In fact, I invite you to find the proof on your own before you read up what it works like in the textbook. That's great. Are we happy now? Well, the ping-pong model has a proof of safety. There is no circumstance at all for the system model to evolve to positions outside 0 and 5 with its control. How much of the control was relevant for that? Not a whole lot, right? I mean, what else could possibly go wrong if we have a proof that a system model is safe? What could have gone wrong is that we wrote down the wrong model for it, and then even if we have a correct proof, if we have that correct proof for the wrong model, it doesn't help our actual bouncing ball become any safer of a ping-pong ball player at all. And that's what the trouble is right now. What does our model say? It says we're in the evolution domain constraint above ground and below 5 all the time, and then, well, great, some funny control happens, but we're then proving that we're always above ground and below 5, which we are essentially by construction, right? If we look at the evolution domain constraint, it's just a slight logical translation of the post condition. So no evolution of the system, provided we start safe, can ever make it to a state outside the safe region. That's a good thing, right? Our system is safe by construction. So René Descartes says he has a proof, but he actually meant to say, no, the system is not a good one because the system is now safe by construction. This evolution domain constraint is essentially the same as this post condition, and that means that no evolution of the system that starts somewhere safe can follow this control and dynamics outside the safe region between 0 and 5. And that means no matter what the bouncing ball is trying to do, he's basically stuck in between the lower bound, 0, and let's just say an upper bound table. And then if the table is infinitely wide, of course there is no surprise that the bouncing ball will stay above ground and below the table, because he does so by construction. But that's not actually a victory of the control, right? It's merely a part of the physical design of the system, and that is asking a very different question. In other words, it's really an assumption that we're making here, that we're following the physics always above ground and below height 5, and why would physics promise to do that? Turns out physics is quite non-negotiable. Making systems safe by construction is a great idea, but only for control, not for the physics. You can't make your system safe by changing the laws of physics, because physics is unpleasantly non-negotiable. If the model is safe because we forgot to include all the relevant behavior of the physical reality, then our correctness statements only hold in the other universe we've been talking about that isn't a real one. Despite all the best control purposes we've got, we just simply don't get to boss physics around. We cannot make this world any safer by writing CPS programs for another universe, since those CPS programs then will only be safe in this other universe to which we first need to teleport somehow. When designing physical models, it is extremely important to make sure that we're actually accurately reflecting everything that physics can do, as opposed to indirectly, in a cheeky way, limit its options. We cannot just stop the world for an event, no matter how big and important the event is to us. Right? The world will go on. We can listen to it maybe, right? But we can't say, as the bouncing ball is trying to fly higher, to say, well, the world doesn't even exist up there. We can split the world for an event still. Right? We can say the world has two options. It's below 5 or it's above 5. We can introduce a second differential equation with another evolution domain constraint that is describing all the motion that's going on above 5 and describing all the motion that's going on below 5. Is this model safe now? We'll ask René Descartes again and his Cartesian demon for help. They say yes, but they still meant to say no, because now we shattered the world because we've been introducing disjoint evolution domain constraints. This only describes the part of the physical world that is less or equal height 5, and that describes the physical part of the world that is strictly above 5. That sounds fine, but the problem is the blue physics is describing what happens above this line, basically. And the red physics is describing what happens below height 5, inclusive. Which is totally fine. The problem is, now it is not possible at all for the system to switch from the part of the world at position less or equal 5 ever to the part of the world where the position is strictly above 5, because all evolutions of this are continuous, all evolutions of that are continuous, and there simply is no continuous trajectory going from less or equal 5 to strictly above 5 without first being at exactly x equals 5, but at height x equals 5, the upper limit of it, this part of the physics world is not yet applicable. In other words, we cannot really follow the right choice, we have to follow the left choice, and the left choice says only follow this below 5. We've made the domain constraints disjoint. So we need to glue the domain constraints together. We need to say the lower red physics talks about everything that's happening down here in this part of the world, and the blue physics, the upper physics, talks about everything that's happening up here, but there actually is a handover point in between the two. The domains are connected. You can be following this differential equation to a height where x is 5, then you can switch, and after coming around the control, you can choose the right differential equation where you say I'm exactly at 5, which is in this evolution domain constraint, and follow this evolution domain constraint for a longer period of time. So we need to make sure we glue the domains together and actually reunite the world, which is always a great idea to do. Is the system safe now? We again ask René Descartes for his help. What we've done, while you're thinking about it, is to make sure that we observe that the evolution domain constraints remain connected. Evolution domain constraints need a lot of care. We need to determine the regions within which the system can evolve very carefully, and disconnected or disjoint evolution domain constraints would disallow continuous transitions. Since our position of the bouncing ball never jumps around discretely in space, it would be impossible for a continuous function of the bouncing ball's position to ever move from one to the other if they're disjoint and disconnected. So splitting these state space into different regions for event detection, that's fine. But destroying the world is not fine. Believe me, it's always a bad idea. You can't even poke these infinitesimal little holes into the time-space continuum because your models won't notice. And if you don't, your system safety analysis will not apply to reality. Let's ask René Descartes and his demon for help. Or for this system model with lower physics and upper physics, which enable transition because there is a point, namely x equals 5, right in between the two. However, the system is now safe above ground and below initial height. So we ask René Descartes for help with the proof. The problem is our event could possibly fire multiple times. Because if we're exactly at height 5, because we've been, say, climbing up here, then we can fall out of this physics, run the event, repeat, we're at height 5, so each of those two options could possibly happen. And we could also follow for 0 time units and fire the event again. To see how that could go wrong, for example, look at this evolution where the bouncing ball is falling, ground controller makes it bounce back up, it's flying up, the evolution domain constraint 5 makes it stop, you stop the evolution, run the control, notice the event that you're between 4 and 5, so you hit it over the head, bouncing ball will be sent down for some amount of time. You repeat again, say in lower physics land. For a short amount of time, the bouncing ball is flying downwards. If you stop the evolution then, you run the control says, am I between 4 and 5? Yes, I am. So you pat the bouncing ball on the bottom because the event between 4 and 5 is true, so you can invert the velocity, but that will make it send back up. Up here, where at the latest you stop the evolution and again hit the bouncing ball over the head, which will be sent down, and so on. So your event could actually fire multiple times, even if you probably only planned to use it once. Well, in this case, there wasn't actually a problem, right? But what about that case? You could send it down and up, drop out of the ODE, run the control. Between 4 and 5, hit it over the head, which will send it down. Repeat, run lower physics again, say. But then only for 0 time units, so that you stop right away and you detect the same event again. Hit it, now over the bottom, which will invert the velocity, send it back up, and you go around, and now if you follow upper physics, you follow this trajectory, which is problematic because you're at an unsafe height right here. So in other words, it is actually quite problematic if our event is responded to multiple times, even if actually really it only happened once, that we're between 4 and 5. How can we make sure that we only respond to the event exactly once? Well, it wouldn't help a whole lot if we rewrote the controller to only act exactly at the height x equals 5, because that's really hard to spot reliably in a concrete implementation. But the only other thing is also that it wouldn't actually help in this scenario. In this scenario, we're exactly at height 5 and respond to the exact same event twice, which will make it fly down, but then again fly up, and then we aren't safe. What we can make happen, however, is to only use the ping-pong paddle when we're currently flying upwards. We would never use it when we're currently flying down. So we change the event detection to say it's still 5 that the event detection in the evolution domain constraint is listening to, but our discrete controller says I'm responding between height 4 and 5. But the ping-pong paddle can only be used when the bouncing ball is currently flying upwards, never when it's flying downwards. Strictly speaking, this model can still respond to events multiple times. You see how? It could still respond multiple times in the case where the current velocity is actually 0. right? Because then it could fall around and do that again, and fall around and do that again, and fall around and do that again. But the point is, in that case, it doesn't really matter, because if you invert the velocity 0 by any arbitrary cofactor, you will hardly notice, because your velocity will still remain 0. In particular, gravity will be taking over eventually and will send quantum the bouncing ball flying down. So you need to pay attention to multi-firing of events. If the same event is detected multiple times, you ask yourself, is it okay to respond to the same event multiple times? Or is it important for your system that you only react to the exact same event only once per occurrence of the event? In our example, that was important because the response of inverting the velocity would do very different things if you do that twice than if you do it only once. And our absence trajectory makes that happen. Let's cover all the facts. What we've got here is a model for quantum ping-pong ball, which we conjecture can actually play ping-pong safely vertically. But let's try and understand better where all the individual parts of the model come from. Some parts of the model are for control purposes. Other parts of the model come from the physics. And the simplicity that we used in the initial part of the textbook no longer quite applies. Namely that discrete is exactly the controls part, and physics is exactly the continuous part. Because some part of this model, even in the differential equations part, is here only for control purposes. At this moment, take a second to try and identify in this model here which of the parts are control, red, and which of the parts are physics, mark them blue. For control, it is very important that you design them very robustly and cover all the potential cases if you have any choices. For the physics part, it's very important that you describe them very precisely and accurately, or at least make sure that you have a non-deterministic over-approximation of everything that physics could ever do. If we do that here, we find the differential equation is purely here for physical purposes, as well as the evolution domain constraint to stay above the ground. That's a physical constraint. Bouncing balls can't fall through the ground if it's solid enough. Likewise, the differential equation over here is for physical purposes. It's still the same. Gravity equations. But the upper limit that the position is less or equal 5, as well as this lower limit that the position is greater or equal 5, these are here exclusively for the pleasure of our controllers, right? We're trying to make sure that physics is nice enough to listen to us when we want to respond to an event, but it's ultimately the controller's responsibility to then do that, which means we have to ensure the world covers all the cases, both the cases of what if this event just happened, but also the cases of what if the event used to happen, but now we're past it and the world moves on. Down here, for example, if we're on the ground, then the bouncing balls will be bouncing back by inverting the velocity. That is discrete, but it's for physical purposes, right? The ground is the ground. It will definitely respond and detect where the bouncing ball is really literally on the ground, and whether it is at height 0. But it's also not like our controllers or the cyberland would have to ever do something like that. On the other hand, this action is introduced purely for the sake of our control. And in that circumstance, it's an extremely good idea that we're not writing controllers that say if we're at the height x equals 5, because this will be very hard to detect and operate reliably, but that we leave some robustness. So for example, we're responding whenever the height is between 4 and 5 and respect anything like that. We're only responding when we're currently flying upwards. Good. Now that we know the individual responsibilities of the control part of the model and the physical part of the model, let's step back and understand that both in the continuous dynamics and in the discrete dynamics do we find pieces of control, but also both in the continuous dynamics and in the discrete dynamics do we find pieces that belong to physics. Assumptions in physics, such as that one, are certainly fine and we're above ground. But assumptions for the sake of control need to be always executed with a decent amount of care because we need to cover all the other cases as well. Having written down such a model, we can again ask René Descartes for help with a proof whether this is really a valid differential logic formula. And it is, and the question is what we do to convince ourselves by a proof that this DL formula is valid. Now we could go off and write an actual sequent calculus proofs for this formula, but that's going to be a lot of effort comparably. Instead, most of what we're doing in this will have a similar structure to the sequent calculus proof for the bouncing ball we did before, where the most important ingredient changing, which is the loop invariant. So let's convince ourselves about the loop invariant and try to see if we can intuitively understand how the proof will then succeed. What could we use as a loop invariant? Well, surely we want the loop invariant to imply the postcondition. How about we choose literally the postcondition? That makes a lot of sense. It's true in the beginning. It does very much imply the postcondition that it is identical to. Is it inductive? Meaning if it's true before one run of the loop, is it true right again afterwards? Well, here, yes. If this condition is true before we run this ODE, it certainly has to be true after we run it because that's what the evolution domain constraint says. Right? The discrete controller changes velocity in all kinds of beautiful ways, but it doesn't affect the position, so it's irrelevant for this question, whether this loop invariant is preserved. What about this part of the differential equation? Of course not, right? Because if we're between 0 and 5 initially, in most of the cases we can't even run the ODE, except when we're exactly at the height 5, at which point we could very well be following this differential equation for a long duration, after which we don't know that we're really still below height 5. So that doesn't work. It's not inductive. What else could we be doing? We could say the loop invariant is that we're always between height 0 and 5 and velocity is going downwards, because if it is, and if we're going downwards, nothing can possibly go wrong here, right? Because we can only follow the differential equation for 0 duration when we're at height 5 at the maximum within this, and our velocity is lesser or equal 0. Because falling means we will connect for actually remain above height 5 if we already are presently at height 5. But that still is not actually inductive. Even if it is true in the beginning, and even if it very much would imply the postcondition, it is not inductive. Can you see where? Well, for example, right here. At this moment of the evolution of the bouncing ball, is our velocity very much positive because the whole point is that we're going upwards. So that won't work. Still, the idea was kind of good, right? That our velocity, if that's less or equal 0, then not much can possibly go wrong in the upper physics half. Let's try another loop invariant, one that combines these two flavors by saying, well, certainly we're in the safe region of the state space between 0 and 5, never above. And also, we don't know about down here whether velocity is positive or negative because, well, it's negative here, but positive there. But if we are exactly at height 5, then our velocity is less or equal 0. And that indeed is inductive. Because, let's convince ourselves of that. First of all, it's true in the beginning, right? We're between 0 and 5. Our velocity is less or equal 0. So yes, this conjunction is certainly true. Whether we are at 5 or not doesn't make a difference here. They do imply the postcondition because one of the conjuncts equals the postcondition. Okay, now let's understand whether it is inductive. First of all, how you would do the proof is to understand that, this for this sequential composition you find here, the second part preserves that we are between height 0 and 5 because it doesn't change the position. So the only thing that we're worried about is what about the velocity. Let's worry about that in a second. For the differential equation, here we also already by construction know that we're between height 0 and 5, so that's going to be easy. And, well, if we are at height 5, then the velocity has to be less or equal to 0. Well, if that's true in the beginning, then because gravity is acting on it, it will only decrease the velocity, so it certainly won't suddenly become positive if v prime equals minus g is acting on the velocity that, if we're at 5, is already negative. Well, if we're not at height 5, we didn't say anything, right, because we could very well be flying upwards. If we're running this differential equation, well, then it's not so easy to see where we're between 0 and 5. But the point is that if this is true before the loop ran, then since this is true that we're between 0 and 5, this must also be true, the evolution domain constraint, that we're at least at 5. That means together this does imply that we're exactly at 5, but hey, our loop invariant tells us if we're exactly at height 5, then the velocity is less or equal to 0, which means that if our velocity is less or equal to 0, and we follow a differential equation that says velocity changes with minus g for gravity, that means our velocity would become negative. That would make a position go below 5, and that we can't have in this evolution domain constraint. In other words, the only evolutions of this then are of duration 0. We must stop upper physics right away and give control a chance. And that means when the controller runs, the only remaining question is not what happens to position because it doesn't change the position, but what happens to velocity. Let's think about it. This part of the control only occurs when we're on the ground, but then we're certainly not at 5, so never mind that. This part of the conditions could happen that we're in between 4 and 5, which is compatible with being at 5, but if we are at 5, then our final velocity will actually be less or equal to 0 because we only exercise this part of the control if our velocity still was greater or equal to 0. Then invert it exactly once, not do that again if it is already less or equal to 0. So we can only make the velocity less or equal to 0, which is precisely what it says. In the else case of this if, which is the one that applies if we have a velocity less or equal to 0 already, nothing changes, but then our inductive hypothesis also is identical to the inductive conclusion. Which means overall, we have an intuitive argument, should do a proper proof, for the safety of event-triggered bouncing ball, where this loop invariant was the most important ingredient. And once we understand this loop invariant very well and have the dynamical axioms for dynamical systems at our disposal, as well as the structuring principles of the sequent calculus, we can very easily conduct the proper proof. Problem: that's a beautiful model, but how on earth would we implement in an actual controller the check whether the height is below 5 all the time? That's kind of hard. Let's summarize what we've learned today. We've seen event-triggered control or event-driven control as one of the very fundamental and important control principles for designing feedback mechanisms in systems. It is conceptually very simple. All we need to do is detect all the relevant events and then respond to each of them correctly, which of course means we need to really list all the events that we're interested in, and in execution does assume that the events are really correctly detected, which is kind of difficult in practice because that requires continuous sensing. The events play a role in the evolution domain constraint, which needs to be true at all the points in time, which is uncountably infinitely many points in time, which are really hard to use control sensors for. So as soon as you find a faithful implementation platform for that, shoot me an email right there. Events also need to be robust, not just things like if my height is exactly 9.8696, then do something, because we'll never actually have that, right? We need robustness built into the system. Events to have surprisingly subtle models, but they can really make design and verification easier. The most important things to keep in mind is the non-negotiability of physics. We can write down the most beautifully amazing and simply to understand models that we want. If they don't reflect physics accurately, it doesn't help us. For example, we need to observe that domains are connected. We need to think about whether multi-firing of events is an issue or not. Still, event-triggered control is a very useful abstraction of reality when the system evolves slowly, but it senses very quickly. Because then even if it isn't really strictly speaking true, it's like close enough. But for systems that move very quickly, say pretty fast bouncing balls, but whose sensing capabilities are comparatively limited, event abstractions can be very bad. Regardless, verifying event-triggered models, even then, can be a very useful first step to do. But you ultimately have to refine it toward a realistic implementation based on the safe event-triggered design. So keep in mind that physics is not the same as control. Most importantly, remember the non-negotiability of physics. Making systems safe by construction, that's the great idea, not for control, and not by changing the laws of physics, because physics is unpleasantly non-negotiable. Despite all the control, we don't get to boss physics around, and we cannot make this world any safer by writing CPS programs for another universe.